Hey guys, um, this video is for Chapter 11 on metals processing. Before I switch over to the notes, I just want to apologize for getting this up a little bit late. I don't know about you guys, but this whole quarantine thing is getting old. Yeah, I just needed to take a break today a bit, hang out with the fam a little bit more than I have been. I saw in my email that a bunch of you had submitted your homework, so thanks for doing that. I'm going to try to get that turned around to you fairly quickly. I want to keep this video to 50 minutes, so I'm going to go ahead and switch over as usual. Oops. Let's share. There we go. Okay. So, Chapter 11 is on applications and processing of metal alloys. And it's a dense chapter. There's a lot of information there. And so my goal with this lecture and with this set of notes is to summarize the information there as efficiently as possible, and to kind of help to get it all in one place so you can see comparisons from one to another type of metal, and then to hopefully reinforce what we talked about in the previous chapter with steel and microstructure formation, transformation, and processing. So for each of these metals, we're kind of going to get a little bit of insight into the structure, or the processing structure properties performance relationship. As we'll go through, you'll see that each metal alloy has a different elemental makeup and a different heat treatment, and that develops unique microstructure, which then gives it its properties. So for each of these, we should see that relationship become evident. And to summarize, right, all of these metal alloys, there's this helpful kind of tree that puts them in the categories. And so generally, we think about alloys as being ferrous and non-ferrous, right? Ferrous is, I guess, a Latin that refers to iron, and so that would be all iron-based alloys. And you think, well, why does one element get its whole dominant category of metals, right? And that's basically due to the abundance of iron on Earth. It's abundant, and so it is economical to work with, right? There's plenty of it. It's also relatively easy to extract and work with, and can be and is very flexible, right? So as we'll see, depending on the impurities and the heat treatments, you can get a wide range of properties. So you can make steels and other iron-based metals work for many applications, and their main downside is that they corrode easily, right? We're all aware of the rusting of steel. And so, but within ferrous alloys, right, we have steels and cast irons. I'd imagine most people are more familiar with steels, but I think the cast irons would make a very nice kind of case study in looking at these 5 different cast irons between microstructure, composition, and properties. And then within steel, you kind of have a couple different categories that are based on the carbon content. Um, so you have low carbon, medium carbon, and high carbon. Um, high is relative, right? We're still talking about um, less than 2%. And then within each of those, you have plain version of the steel, which is basically just iron and carbon. And then you have other alloys where you're adding in additional elements to make them more heat treatable or resist corrosion. And then on the other side of this tree, right, we have non-ferrous. So there we're talking about magnesium, titanium, aluminum, precious metals, pretty much just everything else. Okay, so we covered this a bit. Steels are dominant, but we also have various grades of cast iron, and cast iron is distinguished by having a higher percentage of carbon beyond the solubility of iron crystals to put that carbon into the interstitials, right, into a solid solution. And so these cast irons, as we'll see, are characterized by graphite deposits in many cases, as in addition to carbon-containing phases like ferrite and cementite. Here the carbon content is so high that the ferrite and cementite is not enough to accommodate all of it, and so we see in many of these particles of graphite. Okay. And before I talk a little bit about this table, I'm actually going to jump down and look at the phase diagram again. So this is slightly different here. The phase diagram that we looked at before was for iron and iron carbide or cementite. And this one is actually an iron carbon or graphite phase diagram. The region that we focused on before over here up to 2% looks very similar. The eutectic composition is very similar. I think for the other phase diagram was the eutectic composition was 0.67 weight percent. And you've also got slightly different eutectoid temperature. I think this is slightly higher. But the features are all similar, right? We have ferrite, which has a very low carbon content, and about 2% max solubility for austenite. And so this region looks very similar. And before we kind of had neglected all the rest of it. In fact, we kind of cut it off at 6.7%, which was the carbon content of cementite. But you'll notice in this phase diagram, right, we can go all the way to 100% graphite. And so it's a more pure phase diagram, and that you have the whole thing here. Now, granted, it gets kind of boring once you get above, say, 4 or 5% carbon, right, to the point where they can kind of omit a large portion of it here with this with these symbols. I would point out one thing before we go back and talk about the various cast irons here, is that before we talked about this eutectoid region here, where we had a phase transition from austenite to ferrite and cementite, but we didn't have a eutectic because we weren't transitioning from a liquid phase into a solid phase. For the cast irons, actually, we do have a actual eutectic where we are transitioning, we're solidifying from a liquid to a solid material. And here, as we talked about, characteristic of eutectics is that at that composition, right, you have a lowering of the melting point. And so here, right, you would have typical, steels would melt in the region, of say 1600 C. For these cast irons, at say 2.5 to 4 or so weight percent, you have this significant decrease in the melting temperature, and so now you're getting melting at 1150 C, and so you start to see cast irons being casted, having the molten material poured into a mold, and we'll talk about some of those various ways of doing that later in these notes. But it becomes more doable to cast this material for the cast irons, and that comes directly from the phase diagram here. Okay, and then before we go back up to the table, I'll just look at these microstructures. So the various cast irons, right, they all have about 2.5 to 4% carbon, and depending on the other elements involved and the heat treatments, you can develop one of several different microstructures, and they have differences in strength and ductility. I point out, so the gray cast iron here, you notice they have these spiky flakes of cementite, and this microstructure directly impacts the mechanical properties, because all of these sharp points in these flakes form stress concentrators that make this very brittle and not tough, not resistant to cracking. However, if you add in, I believe it's, I can scroll up and look, but cerium or silicon, I'm going to say, then you can you get these nodular graphite or cementite particles here, and commensurate with that is an increase, right, in the ductility and the, I think, yeah, of nodular, and so that comes directly out of the microstructure. For white cast iron, these are I believe quenched, and so you get cementite particles here, and these are really hard, almost to the point where they're like unmachinable. But if you do a heat treatment where you hold white cast iron at a high enough temperature, you can decompose these cementite particles into these graphite rosettes, and that gives you malleable cast iron. So like is typical with a lot of different metals, if you quench, you get a hard but brittle material, and then heating it to a higher temperature, holding it there, you allow some of that stress to relax, some diffusion to occur, and oftentimes, as you see here, you get a different microstructure that regains some of that ductility at a cost of some of that hardness. And then here you have compacted graphite, where you have kind of a mixture of the others, where you've got some of these harder flakes, and then the more nodular regions. But I'll go up to this table. This is a little bit of an eye chart, but I think an improvement on the text, where you just have kind of paragraph after paragraph of basically facts about these. And what I'm trying to do is kind of put it in a table format here to make it easier to compare and contrast, and look at them kind of in the aggregate of all of this, the steels and the cast irons side by side. And so if we look at, let me take these one column at a time, we look at the alloying elements, right? We have, again, the plain steels, right, are just iron and carbon. And low alloy is less than 0.2% carbon. And you'll notice here that low carbon plain steel, the strengthening mechanism is cold work. Right? If we remember back to our transformation diagrams, you had to quench plain steel, low carbon steel, very quickly to form martensite, right? And maybe a second or something. And so practically, it's very difficult to quench the material that quickly. And we'll talk about this later in these notes. We'll talk about the Hominy end quench test. That you physically can't get the heat out of these parts fast enough in order to form bainite or martensite, much more than right at the edge. Um, and so you don't strengthen low carbon steel through heat treatments, you do it through cold work. You can still deform them and create those dislocations. But the microstructure is going to be perlite because without those other alloying elements, the microstructure can develop very rapidly. But plain carbon steel is common and least expensive because our iron is abundant, carbon is abundant, and you don't need any of those other alloying elements to add into the material, and so it's expensive, or at least expensive and very common, even though its strength is not as high as some other grades of steel, right? But if you are trading off strength, typically what you get is ductility, and so that's what you see here. You have high toughness and machinability, and it's easy to weld, which makes it great for a lot of very common applications like car bodies, I-beams, those sorts of things, right? So it's cheap and it's easy to work with, so it's very commonly used for kind of everyday run-of-the-mill applications. For higher grades of steel, higher carbon contents, right? Once you get above 0.2% or so, you get at mediums, and then as you're pushing the limit, you have these high carbon steels. Most of these are for more exotic applications, and through the addition of other alloying elements, for instance, vanadium or molybdenum, chromium, especially for the stainless steels, the addition of significant percentages of these alloying elements gives these grades of steel the ability to be heat treated. As we saw in our last chapter, these alloying elements slow down the formation of the microstructure, and so you have 50, 100 or so seconds to cool down the material and get around that nose of the time temperature transformation diagram, right? So you can get down to those other microstructures, bainite, martensite, much more easily, right? And we'll see again with this Hominy N-quench test that these higher grades of steel with these alloying elements are much more hardenable, meaning you can quench them and actually get the heat out of the center of a part before, let's say, ferrite or perlite is formed, right? So they are more hardenable. It's easier to get these harder microstructures because of the addition of these alloying elements. And so you see that all of these high strength or alloyed steels are able to be heat treated, quenched, and tempered, in addition to being cold worked and strengthened in that manner. And so you see that they develop microstructures that have the more quenched, the quenched microstructures here, martensite, or in the case mostly, if you're going to get to martensite, generally you're going to temper it because martensite is much too hard and brittle, and so you temper it to get back a little bit of that ductility for toughness and workability. But these are, these more exotic types of steels are for specific applications, gears and train wheels and cutting tools, right? For a cutting tool, you want a really hard material. A die, you need to have a really, really strong material if you're going to be pressing other grades of metal. And then here you have the stainless steel, which is similar, distinguished by very high levels of chromium, and it actually remember when each of these alloys has its own phase diagram, and what's interesting with the stainless steels is you can actually get austenite as a room temperature microstructure. Even though you're used to thinking about austenite as being a high temperature microstructure that transforms, you can sort of so distort the phase diagram through the alloying elements that you can kind lower the austenite region actually all the way to room temperature. But the stainless steels, right, get their name from their high corrosion resistance and their inability, or their resistance to corrosion. Okay, and then I talked a little bit about the microstructures, but we have these several different varieties of cast iron. Again, all the cast irons have 2.5 to 4% weight carbon that gets it to that region near the eutectic on the phase diagram, where you have liquid state at a much lower temperature than you are used to with the than you see with the steels, the lower percent carbons, and they differ from one another based upon these alloying elements. And just like we saw that with the steels, that the alloying elements have a large impact on the microstructure that forms, so is the case with the cast irons here. Right, we see that for the gray iron, right, we have a bit of silicon, which helps to form, which forms these graphite flakes in a pearlite or ferrite matrix, and these flakes form stress concentrators, and so it's not particularly strong, but these gray iron are distinguished by being by having very high damping characteristics, which makes them great, and they're very heavy. So you can make a great base for an industrial machine here, resist vibration, and is relatively inexpensive. If you add, I guess, yeah, there is magnesium. That was the one I couldn't remember. Magnesium or cerium, you can modify the microstructure, and instead of forming these flakes, these graphite flakes, you get these graphite nodes, which are not as sharp as the flakes, and so you don't have the stress concentration factor, so you get an increase in strength here, and so these ductile iron castings can approach the strength of steel. White iron here, this would be similar to maybe martensite, where again you have a bit of silicon here, but they're rapidly cooled, and so when you cool them so quickly, you actually don't form the cement from graphite particles. There's no time. What you get is cementite. And white iron is very hard and brittle, virtually unmachinable, and is good for rollers, as we'll see later in some of this other processing, for rolling out sheets or billets of other metals. But if you take this white iron and you heat treat it, just like we see with martensite, kind of to go to tempered martensite, you can heat treat white iron and go to malleable iron. And what that allows is the cementite gives it a little bit of time and temperature to allow those cementite to take on more of an equilibrium state, where the phase diagram would indicate that you don't have cementite, or at least as much cementite at that region, and so this allows some of that to decompose and form the graphite clusters, and so that allows it to become a little less hard, a little more workable, right, as its name would indicate, with being malleable. Compacted graphite iron has a similar elemental makeup with the silicon. You have these nodular graphite particles that are, in some cases also kind of worm-like, and they have typical tensile strength, but some better properties in some cases, like thermal conductivity or lower oxidation. Okay, so that's a bit of an eye chart, but I think if you go through it, the hope there is that it allows you to compare and contrast those ferrous alloys. Okay, so going down. So the other half of that tree on the first page is the non-ferrous metals, and so steel isn't perfect. For one thing, it's really heavy, so a high density, um, which isn't ideal for many applications. It also has a relatively low electrical conductivity, at least for metals. And as I mentioned before, corrosion is an issue with ferrous alloys. Um, and so you'll see here, as we talk about the non-ferrous alloys, they kind of fall into two categories. Ones that can be cast, meaning they're too brittle to be worked into their final shape, or ones that are ductile enough that they can be wrought and cold worked or hot worked into their final shape. And among the non-ferrous alloys, we have a couple different categories. You have your copper, and I guess maybe kind of buried in here would you would have kind of your precious metals also, but copper stands kind of alone because of its relative inexpensiveness as far as kind of precious metals go. And then you have aluminum and magnesium and titanium. These are, I can think of as sort of aerospace alloys because of their low specific strength, or their high specific strength, right? They're low density. And then you've got, a little more exotic, where you have your refractory metals here, distinguished by really high melting points. Your super alloys. Oh, and I guess maybe, yeah, sorry, earlier I misspoke. Your precious metals, right, aren't buried under copper, right? They have their own category here, the noble metals. And so again, similar to the steels and the cast iron, again, a Callister kind of goes through one at a time, and reading paragraph after paragraph, it's hard to kind of compare and contrast these. So that's why I built another table to kind of take the information that he presents and display it in a way that you can kind of see trends and compare without having to do a lot of flipping back and forth. And so I'll point out some things here. So generally, these alloys are dependent upon the alloying elements, right? There really isn't such a thing as structural aluminum that would be like plain aluminum. Now there are relatively pure grades of aluminum that are used, but typically they're used as like flashing for a building, right? They're not load bearing. To make aluminum strong enough to make, say, an aircraft out of, right? You add in these alloying elements specifically. I think copper is a big one. I think of that one as far as like 7075 T6, which is structural aluminum, or 2024 is also, I think, copper is one of the main alloy elements in there. Same thing with copper. You need the zinc, give you brass, or these elements here, tin, aluminum, silicon, nickel, to form bronze. Let's see here. Okay, the strengthening mechanism that you see with these, there's a lot of different materials here, right? And so you're going to see pretty much every possible strengthening mechanism show up here, right? You've got cold work. Remember, that's room temperature deformation, creating dislocations that impede one another, so that it gets stronger. You have solid solution strengthening, which we have introduced some of the ideas needed to understand that, but I think we don't introduce it until later in this talk, actually. And same thing with precipitation hardening here. Those are similar, in which case you're tailoring the microstructure and bringing out some of these alloying elements in such a way that you can impede the dislocation motion within the structure to an optimal degree. And so the microstructure, so that, a lot of we don't focus on the phase diagrams of these materials, because in a lot of cases we've already covered a lot of the basic features in our discussion of eutectics and also of steels, right? We have multiple phases, the formation of intermetallics, and that same story is repeated for these, just with different alloying elements and different materials. And these non-ferrous alloys are generally used in applications where where steel is not going to cut it, right? Because remember, we said steel is abundant and it's cheap, and so you're going to use it unless there's some reason you can't. And a lot of these come down to weight, right? So especially these lighter alloys, the aluminum, magnesium, titanium, right? You see here that the first application here is aircraft structure, spacecraft. Same thing with the superalloys, right? They're not necessarily light, but they're used in aircraft in turbines because of their high temperature creep resistance and their high temperature oxidation resistance. And then again, the noble metals, these are the kind of the ultimate in corrosion resistance. Kind of that's where the name noble comes from, right? These don't oxidize, like, ever. They're also very ductile. If you remember back when we talked about mechanical testing and about how failure happens, right? You can actually draw these down to a point. They never really fracture. They just sort of turn into a wire, kind of. Okay. I don't want to use up all my time. Okay, so when moving on to processing, there's various different ways that you can take these alloys, these metals, and make something useful out of them. And that's what we mean by metal fabrication. And again, there's a useful kind of tree here to kind of put these in some categories. The main, there's kind of, I guess, three main ways of doing metal fabrication, and that comes down to the ductility of the metal that you're working with. So ductile materials, generally you can form through either forging, rolling, extrusion, or drawing. If you have a brittle material, then you can't deform it, right? It's too hard. You'll get fractured. It's too brittle. And so if you want to form it or make it into a part, you've got to heat it up to a molten state and then pour that molten material into some sort of a mold, whether that's a sand mold or a die, or you can use a foam or investment casting. And then also you have this kind of emerging miscellaneous category here. Welding is a form of metal fabrication, generally to assemble multiple parts, although you could put 3D metal printing also in this category here. Essentially, you're welding the entire part in that case. And powder metallurgy is used for refractory metals, as we'll see here, for metals that it's hard to get them hot enough to melt. Okay, so I've introduced a little bit there. Again, with the forming operations, grab some figures here from the text to kind of quickly illustrate kind of what we're talking about here. There's with the forming operations, they can be done either hot or cold, right? So you have hot working and cold working. The difference here is that whether or not you're above the recrystallization temperature. Remember when we were talking about refining the grain structure, we had this recrystallization where you had this cold working step and then this higher temperature step where you allow the grains to relax and form new grains from that strained kind of parent material. For hot working, you're essentially doing both at the same time, right? I'm deforming it, but it's also hot enough that it can kind of regrow the grains kind of on the fly. And so if you have hot material in this hot working scenario, that allows you to do large repeated deformations because it is recovering basically as you're deforming it. However, remember, chemical reactions are temperature dependent in most cases. And so they happen more rapidly at higher temperatures. And so if I'm hot working it, it's hot, right? And so the surface is going to be oxidizing, unless I guess I can make some special arrangement where I do it in an inert atmosphere, but that's expensive, and so usually it's not, and so you're getting surface oxidation, which will give you kind of a rougher surface finish and also cause you to lose some material during the formation. And then cold working is again, you're below that recrystallization temperature, and so when you deform the material, you're strain hardening, right? So you're adding in dislocations which impede the motion of one another, and so you get a harder material. And since you're doing it at a lower temperature, you're not oxidizing the surface while you do it, and so you get a nicer surface finish. But you can only cold work it so far, right? Because first of all, you got to put more energy in because the material is getting stronger, and also as it gets stronger, it gets more brittle, right? So you could cold work it to a point where it starts to fracture, in which case you would have to heat it back up again to recrystallize, and then you could cold work it again, I guess. And so for some of these other processes, right, you could do them under cold or hot worked conditions, and that would sort of limit how much you can deform and what your surface finish is. But you can have forging both with the open or closed die. I guess forging is more indicative of a hot work scenario. Rolling would be a cold work scenario where you're sort of rolling an ingot out into a sheet, or making an I-beam or some other sort of shape. Extrusion is kind of looks like maybe like with my kids I think about with those little Play-Doh machines, right? Here you have a soft enough metal with a hard enough, strong enough container and a hard enough die that you can, under pressure, force that metal through some sort of a shaped die and extrude, say, a pipe or a channel or something. But generally, this is going to work with your softer metals. Think of your aluminums or your magnesiums, those sorts of things. And then you've got drawing, which would be pulling through a die rather than pressing through a die. And this is sort of how you make wire or tubing. Okay, running out of time. Casting. So if it's too brittle to cold work, too brittle to form, right, then your other option is to cast it. And so you're going to be heating up the material to a molten state and pouring it into some sort of a mold. The different types of casting that generally refer to the different ways of making your mold. You can have a sand mold, which is made in two pieces. And so if you ever have a metal part that has a seam on it, that's probably sand casted because the seam is where the two pieces of the mold meet together. You also, within the mold, typically have a gating system, which is just the ability to get the metal into various parts of the mold rapidly enough before it starts to solidify. You can, instead of having a sand cast mold, basically use a die, which would be a reusable kind of metal mold that you could pour molten material into. But this is limited in melting point. Obviously, you can't have a really high melting point metal being made in a metal die, because what do you make the die out of, right? So you can make the die, say, out of steel, and then pour a lower melting point metal into it, and this is more economic because you can reuse it. Investment in lost foam is similar to the sand casting in that you have a mold that you pour the metal into, except here you're making the mold. You don't have a two-piece mold. You have a kind of a wax object that will become your metal part, and then you pour a kind of a clay slurry around it. It solidifies. Then you can melt the wax out and pour the metal in. Lost foam is similar, except instead of melting the wax out, you just have a foam blank, and when you pour in the molten metal, that foam gets burned away. Continuous casting would be, I guess, where you are creating large ingots of material, say in a mill for later processing. Okay, on the miscellaneous processing techniques here, I already talked a little bit about you have powder metallurgy, and these are for making parts out of really high melting point materials, right? that are brittle. So it's difficult, both to form them because they're brittle, and to cast them because their melting point is so high. And so you can make a part through powder metallurgy where you take a metal, powdered form of that metal, and you press it and heat it into shape. You can also weld material, and here's where you have two relatively cool pieces of material, and then at the seam you heat them up very locally, either with a torch or an arc, electric arc, or a laser, and that creates a puddle of molten material that then solidifies. This can change the microstructure, right? So you might have sensitization to corrosion if you're welding, say, a stainless steel. You can also have this heat affected zone, right? So the nature of the cool down of the weld and the penetration into the seam is important for its overall quality. Okay, I think I got to speed up here. All right, so we have thermal processing of metals. We've talked about this a little bit, and annealing. So if you introduce a strengthening mechanism, right, whether that is through quenching or through cold work, you can anneal. And what annealing is just holding the part at an elevated temperature for long enough time to provide time and temperature for the dislocations to heal themselves. And this buys you back some of your ductility, right? Because remember we said lots of dislocations makes it stiff and strong, and right. So as you heal some of those, you get back some of that ductility. You can have an annealing step to enable you to do additional cold work, because you sort of you heal some of those dislocations, and then you can then flatten it again or bend it again or whatever. And annealing also allows you to change the microstructure. Right? We saw this above with the cast irons, where you can have white cast iron, and then you basically anneal it at a higher, bring it up to higher temperature, and you can change the microstructure by allowing the cementite to decompose into graphite, right there as an example. And here the microstructure is going to depend on what temperature you heat it to, right? If you go all the way up to austenite, then essentially you're kind of resetting the clock on your microstructure. You enable you to create a different microstructure depending on how you cool it down from that austenite region, right? If you do a full anneal and you cool it down very slowly, right, you can get coarse perlite microstructure from the austenite, or you can get other microstructures that we've already talked about. Annealing is diffusion driven. The whole reason we're going to high temperatures is to allow diffusion to happen more rapidly. Okay, so we notice a lot of these, especially the steel alloys, are more heat treatable. What do we mean by heat treatment? We're talking mostly about quench. So what we want is to have the ability to quench martensite, because that gives us a hard, stiff material. But quenching it is harder for larger parts, and it depends on the alloy composition. Right, I've talked about this already. That the addition of those alloying elements get in the way of forming the crystalline phases. Right, they have to be incorporated into the crystal structure, and that strain just slows down the crystallization. And so if you have alloying elements, right, you get a material that is easier to quench. It also depends on the quench medium, right? So you get a quench if your material needs more time to form the crystal structure, and also if you can get the heat out of your part faster. So depending on what you're putting that part in, whether it's air or oil or water or what have you, that medium has a big factor on how fast you can get that heat out. And also the size and shape of the part, right? Obviously a thicker, larger part is going to have interior regions that need to conduct the heat through the rest of the part to get it out. And so that is going to affect how easily you can quench the part all the way to the middle. This ability to be quenched is a property that is called hardenability, and as it sounds, right, it's the ability to be hardened, and it's measured with this Hominy end quench test, which is pretty simple. You just heat up a specimen to austenate to a set temperature where it's well, I guess where it's you have austenate, and then you quick take it out of the furnace, you mount it in a fixture, and then you spray water at the bottom of it, right? So you're quenching the very end of this specimen, and the heat is conducting down through the bottom and then out through the end that you're quenching, and the ability of that heat to conduct and the hardenability of the material will dictate how much of this specimen actually forms martensite, right? And so, so steels that are very hardenable, right, give you a long time to get this heat out, and you should see martensite formation further back the specimen, right? Materials that are not hardenable, not very hardenable, like say low carbon plain steel, you would get maybe the bottom layer quenched to martensite, and then very quickly you would have the formation of perlite because of the low hardenability of those alloys. And so after you do this test, right, then you grind off a portion of the surface and you do hardness testing. And so every so often, closer down to the end, you come down and you do an indentation and you measure the hardness, right? So you have these Rockwell C or Bernal or whatever your hardness tester is, enables you to determine the hardness, because obviously you can't make a tensile specimen from every little point on here to measure what the tensile strength is. So hardness is your surrogate measurement for strength. And what you see here, if you kind of take this nominal end quench test specimen here, is that right at the end, right, you've got high hardness because it's easy to quench that quickly because it's right near your watershed. And then that's indicative of kind of going maybe a path, maybe something like this, right, where you miss the nose here for the perlite. As you go further back, right, you start to hit this, you start to cool down slower, and you pass through this region where you're forming perlite from the austenate, and that is indicative of this decrease of hardness, right? Remember, perlite is a relatively ductile phase, and so as you move away from the end, right, you're going to reduce the hardness. But as I said before, alloying with other elements increases the hardenability because those elements need to be incorporated into the crystal structure as it grows, which is more difficult when you have these other differently shaped, maybe larger elements that need to be incorporated. And so these are, we have a couple of interesting charts here. What you have is the hardness values from several different end quench test specimens. And this group of specimens for this figure here is all the same carbon content, right? This 4-digit number, what you have, the first two tells you what the alloying elements are, and the last 2 digits tell you what the carbon concentration is. So these all end in 40, which tell us that this is 0.4% carbon. And so they all have the same carbon content, except that the blue line here is the plain carbon steel, meaning very few alloying elements, if at all. And so you see that the hardness drops off very quickly, right? Within 3/4 of an inch of the end, you're essentially, well, I guess 20. So you drop by maybe a factor of 2 or 3, or a factor of 2/3. But as you're adding more of these alloying elements, things like nickel or chromium or molybdenum, right, what you're seeing is that your hardenability is increasing, right? So you get up to here at a 4340, and a full 2 inches away from the end of the specimen, right, you're still at 80% martensite, right? Compare that to plain carbon steel, right? It's like 1/8 of an inch, right? So that's what, 16 times as deep, with the addition of these alloying elements. And then also, but percent weight carbon also has an impact, right? So here you're comparing 8620 to 8630, so that's the same alloying composition but more carbon content. So I'm adding carbon, that's making it more hardenable also, right? Same basic reason, right? That I have more carbon to incorporate into the crystal structure, and so that's going to take longer to do so. Oh man, okay, I'm going to go a couple minutes. Okay, and then also you got to get the heat out, right? So the rate of heat extraction is important too. The quench medium has an impact. So here's water versus oil. You can see water is a more effective quench medium than oil. Here we have, as we move away from the surface, or as the bar, let's see here, we have a diameter of the bar, so that would be 50 millimeters. Yeah, we're shifting to the left, so the water has faster cooling rates than the oil does. It's more effective quench medium. And also here, these different lines are related to different locations on a rod, right? So the center would be here, and the edge is the red. So you can see that you get a much faster cooling rate at the surface than you do in the interior, right? For both, but water is more effective quench medium here. And the tensile strength, so as I go to a thicker and thicker bar, right, so that's what these numbers are, right, so we have a bar that goes from 12.5 millimeters to 100 millimeters, right. As we're going to a thicker bar, we're going down in tensile strength because I'm not able to quench the center of that bar to the same hardness as the bar gets thicker. Okay, I'm going to cover this in a couple minutes to try to keep this video within a normal class period or so. And talk about solution, heat treating, precipitation, hardening, age hardening here, which is one of the primary ways of strengthening aluminum alloys. And what you're doing here is you are forming many, many extremely small dispersed particles of a second phase within your parent phase. And this is typical for, like I said, aluminum and copper alloys, also magnesium. And it requires a phase diagram that has a couple of features, right? One is that you have a phase that is relatively low composition, and you need the solubility to be increasing with temperature. And to do a solution heat treat, what you do is you find a composition that can form a solid solution, right? So I need to have a temperature that I can get to get it all in solution, to form a single phase, so and I can form a solid solution, and then if I quench it rapidly, I don't allow the beta phase here to form. There's just not enough time and temperature. So I've quenched it and I've created a supersaturated solution. This is analogous to, say, martensite for steel. And then after that, what I do is I take it back up to a reasonable temperature, right? So here, I might cool it down, quench it to here, and then take it back up, not to the point where it would go back into solution, but then I have just a little bit of time and temperature available for the formation of these beta phase. But because it's the temperature is not too high, right, I can't form very large particles of this beta phase just because the atoms aren't mobile enough for those particles to form very large. And so what I get is a very finely dispersed I guess, distribution of these very small secondary phase particles, right? And so that gives me a lot of phase boundary between the different phases, and that disrupts the movement of your dislocations. and that is thereby strengthening the material through the formation of these precipitates, which are what we call these little particles of the second phase. Right, that's also right. The time after the quench that we hold the material at an elevated temperature is typically called aging. So this mechanism is also called age hardening because it only gets harder as you age it to form that secondary, those precipitates, those secondary phases. And there's a sweet spot, right? You can overage it and actually get a weakening of the material, and that's because, right, the particles could, given enough time and temperature, actually coalesce and become like too big, right? So that you don't have a dispersion of fine particles. Now you have a lesser dispersion of larger particles, and so the strengthening that you had, you lose because your particles become too big. And so there is a sweet spot, and that goes into the particular processing for a certain alloy, right? There's a certain time that you age it for, and then you bring it back down to lock that in. Okay, I'm a few minutes over, but I'm going to go ahead and wrap this up. That's all I had. It's a lot of material, but I tried to condense it in a way that is, I guess, palatable, digestible, makes sense. All right, thanks, guys.